Hello friends, welcome to the ATC Double Cut. In this episode, we are going to take a look at photosynthetically active radiation. And this is one where we're going to go through more information than I typically do in a usual ATC Double Cut. We're going to go through one blog post on the ATC website, and I'm going to talk about how you can know more about the photosynthetically active radiation than you probably ever imagined that you would know. And I'm going to show something on the PACE Turf website, and I'm going to also show a Shiny app. So through all of that, I'm going to give you a lot of resources about photosynthetically active radiation. So if this is one that you're watching on YouTube, you will see some of what I'm showing. If you are listening to this, you may want to take some notes, or you may want to check out the show notes when you're done with this and check out the links that I've linked to, because I'm going to link to a Shiny app that no matter where you are in the world, and let's say if you're less than 66 degrees north latitude, and you are farther north than 66 degrees south latitude, if you're not in an Arctic region, if you're somewhere that is subarctic or closer as you get to the equator, this is going to calculate down to the minute what the full sun photosynthetically active radiation is wherever you are or wherever you're interested in. And it turns out that that's quite useful, and I'm going to explain why that is useful and why you don't really need to measure the photosynthetically active radiation in order to get a pretty good estimate of what it is. Now, it can still be useful to measure it, but as I said, you are going to be able to get really close to what the actual photosynthetically active radiation is just by knowing a few things. So let me get started and not talk about what I'm going to talk about, but actually give you some real details. We can look at a blog post that I will put a direct link to in the show notes. This is a post that I wrote 9 years ago. It has a title, Shade and Sun. And in this, I flat out stated right at the start, I said, shade from trees will often reduce the photosynthetically active radiation, or PAR, by about 80%. And I showed pictures, and this was in Catalonia. I was on a trip to Catalonia and to France and to the southern part of Spain. And I brought along a Spectrum Field Scout quantum light meter, which will measure the instantaneous photosynthetic photon flux density, which is how much photosynthetically active radiation is reaching the meter for any 1 second. And we went to a golf course putting green that had one section in tree shade. And this was just, this is something that we took photos of just to demonstrate that basically shade from trees reduces photosynthetically active radiation by about 80%. I've taken a lot more measurements to confirm this, but we took a picture of the meter in shade, and at the time in sun. So we took it in sun on a green. It's 749 micromoles of photons per square meter per second. It's 749 in the sun. And then an adjacent area on the same green about 30 seconds later, because we just moved directly from the sun into the shade, that adjacent area on the same green but in the tree shade had a photosynthetic photon flux density, or PPFD, of 139. I did a quick calculation earlier. That's about 18%. It's about 18% of what it is in full sun. So full sun was 749. In shade, in this case, was 139. So basically, that's what will happen if you go around, and I'm talking about pine trees, I'm talking about fir trees, or I'm talking about deciduous trees that have leaves on them. If you go and measure the light in full sun, and then you go measure in the shade of that tree, generally it's going to be reduced by about 80%. And that is something that's good to know, because once you know that, now what can you do? Well, if you know what it is in full sun, if you know what the photosynthetically active radiation is in full sun, then you can estimate what it is in shade by just taking away 80% of the light. It's quite simple. And I wrote this in the blog post. I said, it is possible to make a good estimate of the effect of shade and to know just how much PAR is reaching the turf without using a meter. Take this putting green, for example, with part of it in sun and part in tree shade. And I showed a picture of a putting green near Barcelona that has part of the green is in shade and part of the green is in full sun. All we need to know is what the photosynthetically active radiation, which on an instantaneous basis is measured per second. It's PPFD, the photosynthetic photon flux density. If we know what that is in the sun, then we can just take 80% of it away, and that's what it would be in the shade, basically. And do we need a meter to measure it in the sun? Well, yes, to measure it, we need a meter. But on a clear day, about 75% of the radiation that hits the top of the atmosphere will make it down to the ground level. We'll make it down to the surface of the earth. And because we know that on a clear day, about 75% of that's called transmittance. So we would expect about a 75% transmittance factor of light that hits the top of the atmosphere to reach the ground surface. Well, because of that, we can solve this by calculation, because it's possible to calculate how much light from the sun reaches the top of the atmosphere above any point on the Earth's surface. So if you know where you are on the Earth's surface, and if you know what time it is, then you can calculate how much light is reaching the top of the atmosphere right above where you're standing. And then we know that 75% of that in sun is going to be on a clear day. We can expect 75% of that will reach the Earth's surface. And we do various other conversions to convert the light energy into photosynthetic units. But the key thing is that 75% transmittance. And so I'm going to show an app where I've done all of those calculations for you, or I wrote it so that the computer will make those calculations. So all you have to do is choose the day of the year, the location on the Earth that you're interested in, and the time of day, and it's going to calculate in full sun what the photosynthetically active radiation would be at that point on the Earth's surface at that time. And it is, well, if you're dealing with shade problems, it's quite useful to know this and to be able to document it. So I showed also in this blog post that why I say we don't really need to measure it, because I measured all the way from the other side of Valencia, from the southwestern side of Valencia on the southern coast of Spain, up through Catalonia and into southwestern France. I took a number of measurements with my quantum light meter from Spectrum Technologies. I took a number of measurements in full sun at different times of day. And then I calculated at that location, because I knew exactly where I was, so I can look up the latitude and longitude points of where I was when I took the measurement. And of course, I knew the time that I took the measurement. So I calculated what the photosynthetically active radiation should be at that location, and then I calculated what I measured. And I showed it in a chart, and that chart in the blog post, which you might be interested in checking out sometime, shows on the horizontal axis, it shows the calculated photosynthetic photon flux density. And on the Y vertical axis, it shows what I measured with the quantum meter. And it is a linear relationship that is very close to a one-to-one relationship. And it's not a one-to-one relationship, not exactly a one-to-one relationship with that particular meter, but because these meters go out of adjustment so easily, quantum light meters or solar radiation meters go out of calibration quite easily. So in full sun, I almost trust my calculation of what the photosynthetic photon flux density should be. I almost trust that more than the meter. But regardless of which one is the correct measurement, it's almost a one-to-one relationship here anyway. So what that means is whether I measured it or whether I predicted it, I got essentially the same number. So those putting greens where I was standing in full sun and making a measurement, I could measure 749, or I could calculate and get something that's going to be very close to 749 at that particular time of day. So I said that if you are in full sun with no clouds, then you can get a good estimate of the photosynthetic photon flux density from the app that I mentioned, and I'm going to show that coming up. And then I said if there's tree shade, I'd assume that the PPFD, the photosynthetically active radiation, on a second by second basis, the instantaneous measurement of how much photosynthetically active radiation is reaching the ground. If there's tree shade, then you can think that you're reducing that by about 80%, or the PPFD in the shade would be about 20% of what it would be in full sun. That's the effect of tree shade. And I'm going to talk about clouds in a little bit, but I want to jump over and look at the app now. And this is an app that you can find. I'll put a direct link to this in the show notes. I will put a direct link to this in the show notes, and you can also find this on the ATC website. This app has a title. It's a PPFD app. It calculates PPFD and DLI. So, for example, the default settings for it, at least when it opens on my computer, is it opens with a Bangkok latitude and Bangkok longitude, because I have to set it to have a default value. So you want to come in and change your latitude and change your longitude in this app to where you are located or where you are interested. In this case, I'm going to use a location of Portland, Oregon, and I'll use the location for Waverly Country Club, which has a certain latitude and longitude coordinates. So I'm going to go into the app today when I'm recording this. It is June 23rd. We'll play with the hours later. And if we're north of the equator, we put a positive value for latitude. If we are south of the equator, like if you're in Australia or South Africa or South America or New Zealand or something, you go with a negative value. So Waverly Country Club is at 45.45 decimal degrees north. And you see what's happened. It's automatically figuring out the time zone. So it should be figuring out the time zone where you are. So I've left the longitude the same as Bangkok, but I've changed to the latitude of Portland. And now it thinks that we're in Mongolia because it says we're in the Asia Ulaanbaatar time zone. But now we're going to change the longitude. So longitude is how far east or west of Greenwich you are. If you're going east from Greenwich, so if you're going to Denmark or to Russia or to Japan, or to Australia, you put a positive longitude value. If you're going west, like you're going to Iceland or Greenland or the USA or Mexico, then you would put a value that's negative because you're going west of Greenwich. So in this case, Portland, Oregon, the Waverly Country Club location, we're going to go negative 122.65. And it is now updated. The app updates automatically, and it says the app is making calculations. After I've put in those latitude and longitude coordinates, it says the app is making calculations expecting this is in the America Los Angeles time zone, which is correct. That is the time zone that we would have for Portland, Oregon. Now, this works. I think it's really cool because right now it's showing that if the time was 6:38 in the morning on June 23rd, then the expected PPFD in full sun would be 381. That's in units of micromoles. That's in PPFD units, which are always going to be micromoles of photosynthetically active photons per square meter per second. Now, I looked up on Google. Of course, this can be calculated also. And of course, the app is calculating this exactly for those exact coordinates. But I looked up on Google what it says the sunrise and sunset times are in Portland, Oregon on June 23rd. And it said that the sunrise is at 5:22. So if we change our time to be 5:22 in the morning, we should start to get some light, because at night you have no light. At night, the photosynthetic photon flux density is 0 because it's dark. Well, this shows that at 5:22, the expected PPFD is 0. And so if we advance to 5:23, it's showing it's still 0. But I think the reason for this is because the center of Portland, wherever Google thinks Portland is, the sun's going to rise a little bit earlier in the eastern part of Portland, and it's going to rise a little bit later in the western part of Portland. And depending on the longitude, how far north and south you are within Portland, you're also going to get some differences. So this is so cool. For me, it's cool. So 5:23, remember, Google says we're supposed to get light at 5:22. But at 5:23, the app is showing nothing at the Waverly Country Club location. At 5:24, it's showing nothing. At 5:25, it's showing nothing. 5:26, nothing. 5:27, nothing. All of a sudden, now at 5:28 in the morning, it's showing that our expected PPFD is 2.593, or we'd round that to 3. That's very little. Keep in mind that at the middle of the day, we could be up around 2,000. So it's saying that the first photosynthetically active radiation is going to happen at 5:28 in the morning. So that's almost exactly what we get. That's when the sunrise is happening. And then at 5:29, it doubles. It's up to 7.7. At 5:30, we're up to 12.8. That's our PPFD. That's in full sun. If we want to know what that is in tree shade, and I know at Waverly Country Club, which has a lot of beautiful Douglas fir trees around and some other specimen trees, but the Douglas firs are big trees that can throw some shade. So if you're in that shade, you'd take this value that the app is giving you and say, well, we would expect we'd actually only be at 20% of that. The tree shade should be reducing our photosynthetically active radiation by about 80%. And then we can jump ahead to like 12:30 in the afternoon. At 12:30 in the afternoon on this day, it's expected to be 1,853. So there's a lot more light in the middle of the day than there is at 5:28 or 5:29 in the morning. Now, Google said that the sunset in Portland is going to be at 9:03. So let's go to like let's go to 9 o'clock, 2100. It says the expected PPFD is 0. So let's go to 8 o'clock. Let's go to 8:50. So now the app is showing at 8:50, we're at 32.51. At 8:51, so 8:55, we're down to 7. 8:56, we're down to 1.7. At 8:57, it's showing the PPFD is 0. So this app is showing very similar to what the sunrise and sunset times are at that location, and it's already adjusting because the app can figure out what time zone you're in. It's probably going to account for daylight savings time also, which is useful. Okay, so that's a couple things we've looked at. We've looked at a blog post that we've talked about a blog post that explains tree shade is going to reduce the photosynthetically active radiation by about 80%. And also, I've explained that we can measure what the photosynthetically active radiation is anywhere. And so long as it's sunny, so long as we're in full sun, we can figure out what we are in full sun. And we can also figure out what it should be. Well, we can figure out what it is in full sun if we know the latitude, longitude, and the time and the date. And that's easy to figure out. And then what we can do is if we have tree shade, we can reduce it by 80%. So that's good. Now, how to handle clouds. Clouds are tricky, and we can't all go around with a photosynthetically active radiation meter. We can't all go around with light sensors to measure this, but I have done this quite a bit. There were a number of years when I was traveling always with a light meter, and I made a lot of measurements in different conditions, and I came up with some general observations about this. If we're in full sun, then we can just take that full sun number. And then if there's clouds in the sky, so this is something that I would like you to think about, or maybe you'll want to take notes on. I'm not going to show the blog post that discusses this, but I will put a link to it in the show notes. And this is some general rules of thumb for the cloud effect on PAR. And you can tell this by just looking around you. So if you are in a situation where there are clouds in the sky and you can still see your shadow on the ground, then I would consider, and so I've measured this a lot, generally that's going to be reducing the photosynthetically active radiation by about 25%. So you got your full sun number that can be calculated from this app, or I'm going to show you a new feature on Pace Turf that includes this. But you know what you have for photosynthetically active radiation in full sun, and then if you can still see your shadow but there's clouds in the sky, figure that your photosynthetically active radiation is reduced by about 25%. Now we'll move on to another case. You also can be in a situation where you can no longer see your shadow. You can no longer see your shadow. However, you can still tell what direction, where in the sky the sun is. You can tell that the sun is directly overhead, or you can tell if you look up at the sky, you can see that it's brighter over there. You can see that the the sun is in the southwest, or the sun is in the northwest, or something like that. So if you can still see what direction in the sky the sun is, but it's cloudy enough that you no longer see your shadow, that's going to be about a 50% reduction in the photosynthetically active radiation. And then there's the case, which could happen in Portland, Oregon, or could happen in Bangkok, or it could happen in Florida. It could happen in a lot of places when you get really heavy clouds. Maybe you're in a hurricane or a typhoon, or it's a very heavy fog. When obviously you're not going to see your shadow now, but now it's so cloudy that you can't tell, you're not certain what direction in the sky the sun is. You can no longer tell where in the sky the sun is located. If this is the case, you're going to be about 75% reduction in light from what it would be in the full sun condition. So I've described 5 situations, and I'll go ahead and repeat them. Full sun, we can calculate it. That's situation 1. Situation 2, there are clouds in the sky, but we can see our shadow. That's going to be a 25% reduction in light. We have clouds in the sky, but we can no longer see our shadow, but we are able to tell where the sun is located. That's going to be about a 50% reduction in light. When it's so cloudy that you can't even tell where the sun is located, that's going to be about a 75% reduction in light. And when you're in tree shade, this is the 5th scenario. When you're in tree shade, that's going to be about an 80% reduction in light. So we've got an app that can calculate that for pretty much anywhere, unless you're really far north. Once you're into the Arctic regions, this is not going to work so well. But those are very low population areas. So for most people, we're going to be fine here. And you can use the app to calculate what the photosynthetic photon flux density is and the daily light integral for your location. Daily light integral is the sum of all the light from sunrise to sunset, and that's your total photosynthetically active radiation over the course of a day. I want to show one more thing, which is on the Pace Turf website. And let's see. So I put this on Pace Turf yesterday. So for a lot of you are Pace Turf subscribers, and if you're not, what are you waiting for? You can get all kinds of good information, weekly updates from me. But for those who are not Pace Turf subscribers, if you go to the gallery, you can see an example of this. So I calculated for the 15th of each month, which is the average conditions that you would expect in a particular month. So I calculated it for 12 months of the year, for January 15th, February 15th, and so on. For every hour in the day, I calculated for each member's location what the photosynthetic photon flux density is and the daily light integral. So for example, so I use my location of Portland, Oregon, and if we go like January, because the sun is so far south, our daily light integral would be 18, and compare that with July, when our daily light integral on a sunny day would be 62. So that's more than 3 times as much light in July as the grass would get in January. And that's on a sunny day in January, which is a lovely occasion when that happens in Portland. I showed this I showed this zoomed in also. I'm changing my screen for those of you who are watching. I'll show this zoomed in on July. If we look at the June. So we zoom in on the month of June, and what this is showing is for June 15th, which we can take to be a typical day in June, at time 1 in the morning, 2 in the morning, 3 in the morning, 4 in the morning, 5 in the morning, we don't have any PPFD. And then by 6 o'clock in the morning, that goes up. And I'm not showing the y-axis scale when it's zoomed in, but that's on the larger chart. And it goes up to a peak at 1 in the afternoon, and then it declines until we get to 9 p.m. When it goes back to 0. So you can read this chart, and let's say at 6 in the morning, it's close to 250. Then at 7 in the morning at that location, you're at about 500. And at 8 o'clock in the morning, you're above 750. And by 9 o'clock in the morning, you're already above 1,000 in Portland. And because cool season grass can only use about half of the available light, you're already at 1,000 micromoles. You're already about reaching the light saturation point for cool season grass. So that is the kind of detailed information that you can get. You can look this up on that Shiny app, or you can get it from the Pace Turf website. So that is a new addition to the site-specific climate appraisal that's on the top of every Pace Turf member's weather page. So I calculated that. I was inspired to do this by a request, by a conversation that I had last winter with Dr. Cale Bigelow from Purdue University. And we talked about what those normal values would be for maximum photosynthetic photon flux density and daily light integral. And I told him I would calculate it for his location. I calculated it for his location, and I thought, this is cool. It would be nice to provide this to everybody. So this past weekend, I did do that, and I uploaded that into everybody's, all the Pace Turf weather pages. So everybody who's a Pace Turf member should have that under a tab. Let's see if let's go back to the Pace Turf site. If you go to weather, that will be under full sun, PPFD, and DLI. So if you click on that, that is how you can get access to yours. And if you want one of those, well, and you're not a Pace Turf member yet, you know how you can solve that. You can get a Pace Turf membership. All right, everyone. Thank you for listening and watching this. I find it so fascinating to know how much light is reaching the turf. And I hope that I've explained somewhat clearly how you can figure that out. So you can calculate this. There's no reason not to know. You can calculate it on a sunny day. You're going to be really, really close to what it is. And in tree shade, you can estimate it quite accurately. And in particular levels of cloud, just based on whether you can see your shadow, whether you cannot see your shadow, and whether you can tell the location of the sun in the sky, you should be able to figure out what the reduction in photosynthetic photon flux density or daily light integral is. So daily light integral is just the sum of all the PPFD through the day. So the same adjustment factors apply here. I thank you all for listening and for watching. If anybody has any questions about this, I will be happy to answer them. You will also find all kinds of information about this on the ATC and on the Pace Turf websites. I will go ahead and sign off now for ATC from Bangkok, Thailand. I'm Michael Woods. Bye-bye.